I wanted to just quickly put up the qualifications for the award, but the highlight, and I think something that John said, and again, something that I'm very proud of, is the recognition of guiding and developing students. So to me, that's why I do this job. That's why I love this job, working with students. The science is fun, but it's a means to an end, which is to guide and help students. And I've got many of undergraduates and graduate students and former students in the audience, and I thank them for coming. So thank you very much for the support. So one of the themes in my research career is analyzing or modeling electrochemical systems, and I just wanted to put up just kind of a generic thought of what that means. I guess I should also mention that I've recently moved to the University of Cincinnati, but all this work was done while I was at the University of South Carolina, so I certainly owe a huge debt of gratitude for USC helping me throughout my career. Certainly we do mathematical modeling in and of itself, but that is not, a lot of times the perception is you model so that you can predict data, and if the better you predict the data, the better your modeling is, and it kind of stops at that top circle. But really, the modeling helps us give some physical insight to what's going on. And in order to get that physical insight, you've got to compare that to experimental data so that you know whether your models are realistic. If they're not, you may have to go back and rethink of your understanding of that system. So it's a constant interplay between getting the experiments, thinking about what makes sense, trying to model so that you can simulate what's going on, but you're not just trying to match the data. You could do an empirical fit to do that without gaining the insight that's necessary. So all of these are working together, and therefore in my group, we didn't just model systems, but we've done a lot of experimental work trying to isolate phenomenon, doing electroanalytical techniques that can enhance one phenomenon over another phenomenon, and again, try to understand what's going on. And I think people that have practiced in the field for a long time may feel, well, that's just intuitive. I knew that. I didn't need a model to tell me that. And that may be true for someone that's been in the field for 20 or 30 years, but models can help a lot of us learn more quickly when we enter a new area to understand what's going on. So I've worked on a lot of systems over the years. Here's a partial list. My work originally in graduate school and when I first started at the University of South Carolina was on nickel batteries, so a lot of aqueous systems. So that was a case where we did do a lot of experimental data collected data because it was an aqueous system and it was fairly straightforward to do that in the lab. But we weren't just working on cell data, although we did that as well. But once again, we tried to isolate certain phenomena. So we grew thin films of nickel and we tried to get transport and kinetic data with that. And I had the pleasure of working with Professor Newman on understanding the hysteresis that goes on in the nickel material. So that was an example of trying to gain some insight into a very interesting experimental phenomenon that was arising and trying to answer the question, what exactly is going on there? A lot of the work was on modeling and was on batteries and energy storage, but we also did some things on the regeneration of chlorine from anhydrous HCl. That was a project we had with DuPont. Currently, in the last 10 years, we've done a lot of work on hydrogen production in the hybrid sulfur system, once again using models and experimental data to understand what's going on in that system. And a lot of modeling on fuel cells, in particular multi-phase, multi-scale modeling of porous electrodes using the Lattice-Boltzmann method. And there, Vach Jampali has been I've learned a lot from him on how to do this multi-scale modeling and taking a system that's computationally very complicated and being able to get something that you could actually get some decent answers with. But today I'm just going to focus on, in this short 20-minute talk, the lithium thionyl chloride battery and really emphasizing how we handled volume change inside porous electrodes. So it started with the lithium thionyl chloride, so I kind of want to introduce that and then talk about how we handle volume change. And before I get into that, I'm just showing up kind of a simple schematic of a spiral wound cell for a few reasons. One, this is from a paper from Ralph White. He was a mentor of mine for, again, my 28 years at the University of South Carolina, so I owe him a big gratitude for all the mentoringship he did with me, as well as my PhD advisor, Peter Fedke. Learned a lot from them and how to treat and advise students and help them along in their careers. But the other thing that this shows is, again, a simple illustration of a spiral wound battery. So typically we look at what's happening inside of one sandwich of an anode, cathode, and separator, and we focus our modeling efforts on that. But we always have to remember that it's inside a bigger system. So in this case, a spiral wound cell. And one of the things that we modeled that I listed earlier was thermal properties inside a cell, or the thermal management inside of a cell. So in here, the electrochemistry is actually occurring over a fairly small distance, so more on the tens or hundreds of microns, where this battery is maybe a few centimeters, and if you put it in a cell pack or inside of an electric vehicle, it's even much bigger than that. So the thermal effects tend to be on very different scales than the electrochemistry, and again, marrying the thermal and electrochemical effects can be quite challenging. And so we worked on that as well. But again, always remembering that we're looking at some kind of large battery system, but we always put the electrochemistry, or we model a single cell, and here's an example, and this is a lithium thionyl chloride system. So in this system, it's a very high energy density primary battery, so you don't recharge it, but it's got a lithium anode, it's got a separator, and then a porous cathode, and the key reaction that we're trying to model on the cathode is the lithium chloride, which is a solid material. So that's precipitating inside the porous electrodes. So this is a little different than the lithium ion electrodes that I'll show a little bit later, where we're intercalating lithium into the active material, and that solid phase is changing. Here, the porous electrode, the porous carbon doesn't change, and we're depositing material at the site of the reaction. So wherever the reaction is occurring, you're getting a lot of solid material to deposit. So that was the key thing from a understanding that we were trying to understand, is depending on the rate and operating conditions of temperature and so on, and design, how this reaction distributed throughout this porous electrode. And so we did a series of models on this. There's also very interesting to look at the flow conditions that occur. You've got a headspace that's got some excess liquid material that has to flow through the separator and the porous material, so it becomes a very interesting two-dimensional process, and we did the flow distributions and so on in the cell. So once again, you can get some insight into what's happening inside the cell, which would be almost impossible to visualize otherwise. So if you're confident that you've got the physics right, you can look inside and see some interesting things. So here's an example of some plots of the electrochemistry. So here I'm showing the reaction distribution. Another thing that's very difficult to get experimentally, but again, if you're confident in the physics that you have in the model, you can look at it and understand what's going on. So what we have here is our separator and the beginning of our cathode. So this is our porous region. We have a reaction rate going on inside that cathode, and this is just different moments in time. So from 0.1 hour to up to 30, and then there's extending through time. But the main thing is we have this non-uniform distribution in reaction rate, and the reason, as we familiar with porous electrode theories, you get reactions that are occurring at the front face because it's ohmically limited in the electrolyte phase, so you get a lot of reaction at the front. Now remember, this is wherever the reaction is occurring, you're depositing a solid material. So all of a sudden, the front of the electrode, not only did you have a lot of reaction there, but that's where the porosity starts to drop and accentuating the non-uniformity. So early on, you may have something fairly uniform, but it becomes very non-uniform over time because, again, you're closing the pores off inside the cell. And there's an interplay between the experimental data that you're collecting and the models. And this was work that we did with Sandia National Lab. They had a lot of experimental data. They were interested in understanding these high energy density cells over a very wide temperature range, from minus 55 degrees Celsius up to up to even to 75 degrees Celsius. So once again, a lot of data that we collected, but here's kind of an example at the end of the day where you've gone into the lab, or they did a lot of work on transport and kinetics in individual cell studies. You put that into the model and you get some good agreement between the experimental data and the model. You feel good that you've got a lot of the physics in there. There's still some parameter estimation that you're doing, but again, you're doing it over a very wide range of discharge currents, temperatures, and so on. And so again, you feel like you've got most of the physics, although maybe not all of it in there, and it gives you some gratification that you can maybe get some understanding of what's going on. So with that understanding, one of the things that we can look at, again, related to the reaction distribution, is what does the porous electrode, what does the porosity distribution look like? And this is the porosity distribution at the end of discharge. So when the battery, the voltage dropped off the cliff and you can no longer use it, and I show it for 3 different temperatures. And again, what we see is that at the front end, the battery died because the porosity went to 0. We've completely filled the pores in the front. You can't get ions into the back of the electrode. Although in the back of the electrode, there's still a very high porosity, meaning there's still a lot more reaction that could have occurred, and hence why the capacity drops off dramatically as you decrease the temperature. So at these very low temperatures, again, you had a lot more capacity left that you weren't able to access. At room temperature, you almost access the whole amount. So again, there's some insights that you can get that experimentally you would have a hard time measuring. So one of the things, and that had troubled us a while, is we think we had a lot of the physics right, but one of the things that that was troubling was the fact that when they made these cells at Sandia, they would roll them up. It was a spiral wound cell, and they'd put it in a can, and they'd fill it with electrolyte, and it was fairly loose in the can. And then when they were finished with the discharge, the can was bulging, and you couldn't get the active material out of there anymore. So clearly there was volume change going on. In other words, the can was, the porous electrodes were expanding. However, in the model, which was fairly common in a lot of porous electrode modeling where the porosity is changing with time, you relate the porosity change to the reaction rate J, and then the volume of what's depositing, in this case the lithium chloride. And so it was saying any deposition that was occurring, again, was filling pores, but then what was causing the electrodes to expand. So we started thinking about this over time, and we looked at a kind of a generic system. Again, what I just showed you in lithium thionyl was depositing material, but here we changed the picture a little bit and made it more like an insertion electrode, and we said, what happens if we have this porous electrode filled with balls, ideally, and we inserted lithium into those balls and they expanded? What would they do? Well, again, the equation that I showed before would say that if this ball got bigger, it would go into the pores and the porosity would go down, where the volume of the can doesn't change. But again, we know, or the volume of the electrode, but we know from experiments that volume does expand. And so I don't know if it's clear from this picture, but those balls got bigger, the porosity got smaller, but also that box grew a little bit. All right. So when the ball expands, it can do one of two things. It can fill a pore, or it can expand the electrode. And the question was, which one was it? How much goes into each one? And how do you quantify that? And we, for the longest time, couldn't figure out how to do that. So we just, but we we went at modeling it and we just said, well, the volume, you have some initial volume and initial porosity, and then you'll have a porosity that's changing, and you also have a volume of the electrode that's changing, and that's related to the current that's going on. And so how do we model that? Well, instead of just relating the reaction rate to the porosity change, we're going to add a velocity term. In other words, the electrode itself is moving. So here we have the rate of change of the solid volume, or in other words, the porosity change, the velocity of the electrode, or the expansion, the displacement of the electrode, and then again, this is the solid balls expanding. And of course, a lot of people have looked at what is the stress and strain that's built up in a ball that's expanding, or active material that's expanding. We wanted to extend it to the porous electrode. So we were able to relate that velocity change to a volume increase, and it turns out that middle term is fairly small. So again, we basically have a porosity change, and a expansion of the electrode is related to the local reaction rate. And for the longest time, we couldn't, again, figure out exactly how to divide that out, because what we've done is add another equation or another unknown, but we didn't add another equation, right? We've added this, the volume expansion, the expansion of the electrode. We need another equation for that. So we couldn't figure out the relationship between the porosity and the volume change, so we just said, let's, and this was Partha Gomadam that started this, and he's currently at Medtronic doing battery modeling for medical devices. And he said, well, maybe we can't predict it, but let's just assume a value and split it between these two. Let's just say, oh, it's 50% volume change, 50% porosity change, 50% expansion, or 25%, 75%, or whatever number you wanted. We call that the G parameter. I'm not sure why he called it the G parameter. Maybe he ran out of letters. But that'll come up in a slide later on. But it just says what fraction of the volume goes into those two things. And so once again, in modeling, sometimes you throw up your hands and you say, well, I can't predict that, but is it even important? Does it really matter how I divide this up? And I can vary that between 0 and 1 and see if it's important. And of course, I'm talking about it because it turns out it is important. So then we started talking to some of the mechanical engineers at South Carolina, and they said, oh, that looks a lot like rock mechanics. In rock mechanics, they have the same problem. They have a porous bed. Dimensions are a little different. They have a big porous soil layer or surface layer with rocks. And in their case, the rocks expand usually from thermal reasons, but the rocks get bigger and smaller. And they too want to know if that rocky soil is expanding or if the pores are just getting filled up. All right. And he said when you do that, according to rock mechanics, you get this simple relationship that is a logarithmic relationship between your stress-strain curve. It's basically saying that if the rocks, in their case, if the compressibility of the rock is constant, you should get an exponential relationship between stress and strain, and you balance that between what's holding it back. So in our case, the can that all the active material sits inside. And so now we have a relationship between, an additional relationship that tells us what does the volume change do and how does stresses that build up inside that. And that's got to be balanced then by the can. So if the can is rigid, it can't move, everything's going to go into porosity change. If the can, like a pouch cell, doesn't offer any resistance, then the material will expand. So here's some examples of that. And here is a low rate discharge, meaning everything is uniform. And again, another nice thing about modeling is you can do things that maybe aren't, quote, physically realistic. So this is a battery that only has one electrode. But we can, again, at least understand what's going on before we expand it into an actual cell. And so here is the example where the can will not expand. So it's a very, very rigid can. And therefore, when those balls expand, they just fill the porous region. On the other end, if there is no resistance to expansion, then all that volume change, there'll be no porosity change. And so if we look at the prediction of porosity versus state of charge, we find out that, again, if it offers no resistance, the porosity will remain constant. If it's a rigid can, it'll change linearly with time. And in a more realistic can, aluminum that has fairly rigid, but it's not completely rigid, you will get a distribution. You will see the porosity is changing, but not linearly with time. And this swelling coefficient G, again, when we first did this, we just said, well, that G parameter is constant. Let's play with that. Here we see that that G parameter does change during discharge. So when the can is packed fairly loosely, even if the can is rigid, it's going to be a dimensional change. Most of it will go into dimensional changes because there's not a lot of resistance, although there's some. And then later on, when the can gets pretty full and it's really pushing against the walls of the can, most of it's going to go into porosity changes. And again, that depends on the relationship between the compressibility of the active material and the can itself. And how significant is this? Again, even when we assumed G was constant, we realized it could be quite significant. If the can doesn't offer any resistance, the one on the right, the ionic resistance, which we can measure by relating it to the porosity, actually drops a little bit, and that's because the cross-sectional area expanded a little bit. But if you force all of it to go into porosity change, the resistance goes up dramatically. Bergman coefficient, if it changes to the 1.5 power, again, it's very sensitive to porosity. So certainly, where we are on this curve is going to dramatically affect the resistance, in this case the ionic resistance, and in fact the cell potential. So here's, again, a fictitious one electrode battery. And so we're just seeing what it's doing relative to a 0 point with a Nernstian equilibrium potential. And again, when most of it goes into porosity changes, the resistance goes up exponentially and the voltage drops off fast. If there's no resistance, you just have a nice Nernstian relationship between the two. So again, that gave us some insight. It also showed us the importance of properly capturing the porosity change. And but now we want to put it in a real in an actual battery. And of course, this is actually more extreme than you would expect, because in a real battery, the anode's probably expanding and the cathode's contracting and vice versa. So one is going to kind of push against the other one. And here we didn't have that other case. But what we then did was, okay, let's put this physics that we just are comfortable now, the equations that relate the expansion and the porosity, let's put it into a real battery model. So Taylor Garrick did a DOE fellowship out at Lawrence Berkeley Lab. They had a lithium-ion battery model. It had all the bells and whistles and had transport and kinetics and on and on and on. So we didn't have to reinvent that wheel, and we just put in, or Taylor put in the rock mechanics portion of it. And now we were able to extend it to not just these low-rate uniform fictitious electrodes, but now kind of a real system. And what we see in, qualitatively anyway, what we see in a lot of porous electrode battery modeling is things, again, and similar to the lithium thionyl chloride, the porosity is fairly constant in the beginning, and then it gets more and more non-uniform, and then all of a sudden gets very non-uniform. And if we look at the reaction distribution, it's not uniform, but it's fairly constant throughout. But once we've used up all the material in the front end, now we actually get a wave front that moves through the electrode. A little different than the lithium thionyl chloride, which plugged the front. Here, we just run out of active material at the front, and then that wave moves farther and farther back until we hit the cutoff voltage. So here are some discharge curves, again, from this lithium thionyl chloride, or the lithium-ion battery model from LBL. And we see kind of the same thing we saw before, in that if it's the more rigid it becomes, the more the less capacity you're going to get out of the cell. However, now we can understand a little bit more that it is rate dependent. And that is, if you do it at very high rates, you actually don't see much effect. And that's because you haven't gotten a lot of capacity out of the cell. Most of it's been withdrawn before you had a chance for a lot of these pressures to build up inside the cell that will cause where the rigidity, before the rigidity can actually play a role in the process. So now we can understand not only its rate capability, but then how are we going to design the cell, how are we going to, what kind of active material we're going to put in there and so on. I guess one thing I didn't mention is this, all the results I showed to date are for active material that expands by about 100%. So silicon anodes can expand 200-300% or more. So these would be maybe some hybrid materials. And we're currently working with General Motors, who's looking at being able to vary that by varying the amount of carbon and silicon they put inside their electrode. So you can vary the fraction of what percent expansion you have, and then you can use the models to say, depending on the rate that I want to get out of these cells, this may tell me what kind of material mix I need, what kind of anode cathode thicknesses I need, and so on. And so both Taylor and Drew Pereira are going to be presenting more about this in an actual cell on Thursday. So you can hear more details on that. And one of the biggest changes we've done with these actual cells, not only that we can vary the active material and see what that does to these profiles, but also up to this point we're assuming that the compressibility of the active material is constant, as I said earlier with rock mechanics. But really what you want to do is take a porous material and get the stress strain curve for that material, because that's going to depend on the porosity of the initial makeup, what is your binder, and so on. And so once again, GM has made these electrodes, measured the stress strain curve. That's going into the model, and we can further improve the predictions. So, kind of in summary, again, mathematical models are used not only to predict what's going on, although that certainly is a benefit of it, but it's really to gain insight, especially as you're learning a new field, and so that you can help the design and operation of these electrochemical systems. You can also just play with assumptions. They don't necessarily have to be realistic or not, but you can say, what if that phenomenon doesn't exist? Does it really change the prediction of the cell? And so you can test phenomenon, isolate them. Nothing's going to break or blow up if you make something too big or too small, and you can play with that stuff. And then in this particular case, we were able to integrate some solid mechanics with some electrochemistry to understand these volume changes, which are going to become increasingly important with these new advanced battery systems. And then finally, I'd like to acknowledge, and I could acknowledge lots of people, but I want to finish up with acknowledging my students, my both current and former PhD students. And I've talked about a few along the way, and I want to highlight them individually, but I do want to pay a special gratitude to my first 4 PhD students. My first 3, Mukul Jain, who did all the lithium thionyl chloride work, Kamal Jha and Satya Mantapalli. I wouldn't have gotten tenure without those 3, so I thank them immensely. And then Venkat Srinivasan, who, while I was on sabbatical at Berkeley, held my lab together and kept things going. And he was an integral part of the work we did with Professor Newman on the nickel active material. And with that, I will take questions. Yeah, so I mean, a constant G coefficient is a little, that's a pretty big assumption that it's constant. And we see even in the simple model where we have a constant compressibility, it changes throughout the discharge. So we have to be able to predict what the stress strain curve is, which I think is what you're getting at maybe. I'm not, we're not looking at the physics at that level, so we're empirically getting the relationship between stress strain, but it certainly has to do with the friction, between the active material and the binder, and all the physical things that go on as that electrode is being compressed. And that's handled empirically. That we're not trying to predict a priori. Yeah, so you would have to, so if you knew what was happening, and again, a lot of people have studied the individual active material expanding, contracting, you'd have to put those physics in, so that's not here. This is assuming it's completely reversible, but that you could add that just like any other phenomenon. You could add an SEI layer, you could add the particles breaking in size. That wouldn't change the physics, that would change your stress strain curve, so you might have to change that over cycling, but the physics is the same. Yeah. All right, well, thank you very much. I appreciate you